record. So according to the Snell's law, so here we have about the Snell's law. Snell's law is specially for the refraction. Okay.
Okay.
So
Sir, I don't think we did light. We only finished the first part of waves.
of course, but see, the light, it's nothing but an electromagnetic wave. So even if we start from this point, okay, regarding the light, okay, then it will be also comfortable for you, because since in this portion I am just only observing most of the refraction type. Okay. And in light, basically we are going to learn reflection, refraction, total internal reflection, if it was given in any of the paper, then we will see. Otherwise only these two portions are there. So
you
reflection,
can check if you want. I can check if you want, if it's in the syllabus.
yeah, please just check it. Okay.
Okay, just a second.
Yeah, sure.
Um,
I guess you just send me also a screenshot of
okay.
it. Yes, I have your screenshot.
Yes.
Let me open it. Okay, so
No, that's for my test. I'll tell if it's coming or not in the syllabus, the
okay,
specification, right?
yeah.
So in light, there is reflection in light, where it's described the formation of optical image by plane mirror and give
Okay,
characteristics.
okay.
Recall, use law, angle of
Angle of reflection or reflection.
virtual image,
Okay,
refraction of light, where
okay,
we need to know experimental demonstration of the refraction of light,
okay.
the terminology, angle of incidence, and angle of refraction to
Okay,
describe the passage of light through parallel side transparent material,
okay.
give the meaning of critical angle, describe internal and total and internal
Internal
reflection,
reflection. Okay, great.
use the definition for refractive index,
Hmm.
recall sin I over sin R, and
That is a
recall
Snell's
1
law.
over
Okay.
C. And
Hmm.
then thin converging lights, a thin
Okay.
converging lens,
Okay. Yes.
and
Converging
dispersion.
lens and divergent lens. Yes. Okay.
Yeah, and
Hmm.
dispersion of light.
Okay. Dispersion of light. So up to the prism. So see, you have
Yes.
here mirrors.
Yeah.
So what we are going to cover. So first mirrors, especially you have been given plane mirrors.
Yeah.
And do you have spherical mirrors?
Spherical, no, just plain mirrors.
Okay. So in the reflection, we have a plane mirror. So let's start from this plane mirror. So first of all, the meaning of reflection. So what does it mean by reflection? So the meaning of reflection, it means that whenever the light came back in a same medium after striking any of the opaque surface, okay, whenever we incident the light on any of the opaque surface, and when it comes back into the same medium, then it's called the reflection of light.
Okay.
So we need a non-transparent or a shiny surface which is required,
Yeah.
mostly a silvering surface that can be also worked. This is the normal. And here if I incident any of the light, so let me consider this my incident light. And here is your angle of incident. So let me call this theta I. That is our angle of incident.
Okay.
In many of the reference books, you will see that here it is also given as an reflection angle or the incident angle. Okay. It makes with the normal in many of the reference book, and in many of the reference book, it is also given like this with the horizontal surface where we are reflection and refractions are takes place. But it's a one and same thing. Okay. Our answer is not going to be changed.
Yeah.
So this is our theta I. And when this light reflect, so this angle is called our angle of reflection. And As for Fermat principle, both the angles are same. Angle of reflection. So both this angle are same. So this is the law of reflection. See, whatever the mirror we use, whether it's a plane mirror or even it's a spherical mirror. So in spherical mirror, what happened? We have converging mirrors as well as we have the diverging mirrors, concave and
Okay.
convex. Okay. So even
Yeah.
though this angle of reflection and angle of incident are always same, as far as the
Yeah.
reflection is there, so we have these two angles are always same. So if this angle is 35
Okay.
degree, so this
Then
our
that will
angle,
be satisfied.
yes, that will be also a 35 degree.
Okay. Sir, do you just mind waiting for 2 minutes? I'll get my charger. I'm out of charge.
Okay. Your charger or your laptop charger?
My laptop charger.
Okay.
Okay, so we can continue.
Okay, great. So this is the simple law of the our reflection. Then in mirrors, how the image will form. Okay, especially this plane mirrors. So if I consider this is my plane mirror and this is our principal axis. Principal axis. So if any of the object is somewhere here,
What is the principal axis?
well, this is the imaginary axis, first of all, on which we are going to obtain all our objects as well as our images. Okay, so
Like,
you
can
can
you
draw
give an
it.
example?
Well, it is not like call an example, but the thing is, whenever you obtain or whenever you
It's
want
like an
to,
imaginary line.
yes, it's an imaginary line, and whatever our objects, image, we can draw on this imaginary line. So that's why this line we call it a principal axis.
Like in the drawing, it's between the mirror and the object.
Yes, it is between the mirror. No, actually, we can say that you can draw a path on which you can put your object on it.
Okay.
Okay. So it is just passed through the mirror and you can pass it from the any of the point of the mirror. Like if you have your mirror here and if you want to make your principal axis here, you can make it. Even if here is your principal axis and you can put your mirror here also.
But what is the point of the principal axis?
Well, the only point that whenever we need any of the object distance or the image distance, okay, so we need a surface where we are
Yeah.
going to place our object. Okay,
Yeah.
so that surface is actually our principal axis.
Okay. So,
Hmm.
example, if I'm standing in front of a mirror, the ground will be the principal
Yes,
axis.
your ground will be the principal axis and that axis will also pass through the mirror. And even sometimes
So
it
the distance
won't be.
from me and the mirror will be the same for the reflection.
Yes, but how it will be same? Our question is how it will be same. Okay,
Yeah.
so if I draw a parallel ray from this head, okay,
Yeah.
so it's a 90 degree of the angle of incident, we can say that.
Yes.
So our angle of reflection is also going to be the 90 degree. So it will be just reflect back. So we can say that at this 90 degree angle of incident, our light ray will retrace its path. Can we say that?
Yes.
Okay, but this will happen only at this angle. Okay, it won't happen for the other angles. So
Wait, could you repeat it again?
yes, if our angle of incident is 90°, okay,
Yeah.
only then our reflected ray will retrace its path. Okay,
What is retrace?
retrace,
Like
it
how?
means that,
What do you?
well, you can say that the path which has been followed by the incident ray, the same path will be followed by the reflected ray. Like if you are going to your school, okay, and
Yeah.
if you just return back on the same path, exactly same path with the same angle and same number of steps, okay, and the same directions and the same turns, it means that you are retracing your path.
Okay. Okay. Yeah.
Okay, and this
So
thing
it's the
happened.
same
Yeah,
path.
yes,
Okay.
same path, but the proper word is called the retrace.
Retrace. Okay.
Yes, and if I draw another incident ray somewhere here, okay, and the point from which our principal axis is passed is called pole of the mirror. Okay, it's called pole of the mirror, another name, okay, a significant for our plane mirrors. Okay, like here, like you can say that, so here we don't have any mirror, or this
Yeah.
principal axis is not passing through this mirror. Of course it will pass, okay, but you just have to extend your mirror like this. So this can be considered your pole, yes or no?
Yes.
Okay, and same thing here also, okay, just extend it, so you will get your pole. So
Okay.
if I just incident array to this pole like this, so we know that this is called my angle of incident.
Yeah.
So if this angle is theta, then at the same angle this light will reflect back.
Yes.
So it is called the reflection. Okay,
Okay. Got
now,
it.
yeah, but now the main question is arise. Now see, this ray which is just turns back, so it goes in this way, in this direction. This reflected ray is goes in this direction. Okay,
Okay.
see, image is only formed when two reflected rays will intersect each other.
Yeah.
Okay, and here, as you can see that none of our reflected rays, okay, we need at least two reflected rays must be intersect to form an image. But here, as you can see that this reflected rays are not intersecting, will never intersect even up to we just want to the infinity,
Okay. Yeah.
as you can see that. Okay, so how we will get the image? Now see, if in the direction of reflection, in the direction of reflection, if the rays are not intersecting, then we must go into the reverse direction. We must go to the reverse direction, means in front of the mirror, as you can see that these two rays are never intersect each other, will never intersect.
Mm.
Okay, so
Yeah.
I must go behind the mirror, yes or no?
Yes.
Okay, so let extend this light in this way. Ooh, so here, as you can see that in the backward direction, these two rays are actually intersecting each other, yes or no?
Yes. Yes.
So
And the
here,
object is formed there. The
yeah,
image is formed
image
there.
will form. Yes, image will form. So here is your image.
Yeah.
Okay, of course this is smiley image, so this should be also the smiley image.
Yeah.
Otherwise what happened, like if you are standing in front of your mirror, okay, you are smiling and your image is not smiling, instead of that he is just staring you like an angry look, like that.
Yeah.
Then what happened? See.
There's a
Hmm?
ghost probably at his
Yeah,
house.
definitely that would be the ghost. Okay, so this is how our image is formed, okay, with the help of the reflected rays. And
Yeah.
the important thing is the from mirror to object, this is called our object distance. It is denoted as a u as our object distance.
Okay.
And this is called our image distance. Let's call it v. So v is our image distance. Both are measured from this mirror, both are on this principal axis. Okay, this is the importance of the principal axis. Okay, you can place your object on the principal axis, so you will get your image also on the principal axis.
Okay, understood.
And from this diagram, you can simply conclude that this object distance and image distance will be same or different,
Same.
of course. So we can say that this object distance equals to the image distance. But see,
Okay.
how is your image? Whether it's a, we can say, straight image or it's a reversible image.
Reversible image.
Just see it again. Is it reversible? Like if I, my stylus pen is
Oh
like that.
no, no, it's not reversible, but
Yes,
then
it's
it
a
is
straight or erect. The
yeah,
proper word
it's
is
straight.
erect. Okay.
Yeah.
So since it's an erect image, okay, erect, it means a straight. Like if
Yeah.
my object is straight, then my image must be straight. That is called the erect. And if reversible, so it will be totally reversible. Like my stylus pen is like this. Okay. Then
Yeah.
image should be like this. Just
Yeah.
tip. Okay. So this is called a reversible images. But if I
Yeah.
got this kind of images, it means that it's an erect image or a straight image.
Yeah.
Okay. Now, since it's an erect image, always remember that if any image is erect, then it's always a virtual image. Erect images are always virtual.
Okay.
So erect image is a virtual image. Okay. Do you have sign convention?
Yeah, we have sign.
Okay. Let me show you the simplest way to remember all the sign conventions. Always remember that this sign
I think we
convention.
only have one. Sin I. No, I mean we have two. Sin
Mhm.
I over sin R and 1 over sin C.
Okay, I'm not talking about that. That was the
Oh.
refraction part in
Oh,
Snell's
okay.
law and the critical angle. I am asking about the sign convention. And do you have mirror formula? I don't think so. It will be because since you don't have a spherical mirrors, so I don't think there will be a mirror
No,
formula.
I don't think we have sign convention.
Okay, that's good. But mostly maybe in lens. Okay, so that we will learn when the lens part will be there. Okay, so this is
Yeah.
about the plane mirror, the simple thing.
Yeah.
And one more thing, if it is asked that the magnification, so the magnification, the formula of the magnification is nothing but the image distance over object distance.
Okay.
And here both are how much, how same or differ? The object
They're
distance and the image distance are for
same.
the plane mirror is always same. So
Yeah.
if it is same, so I can simply consider is V by V or U over U. So my
Yeah.
magnification will be 1.
Over 1.
So for the plane mirror, your magnification is always 1.
1.
And this magnification 1 also indicates that the height of the object and the height of the image are also same.
Okay.
Okay, as well
And
as.
sir, also
Hmm,
there is something about the plane mirror.
hmm,
I'm not sure what's the word for it, but then
hmm.
it's like opposite when you see the mirror, right?
It's called lateral
Like,
inversion. It's called
yeah,
lateral
lateral.
inversion. Yes, lateral, it means sides. So your sides are going to be reverse. Okay,
Okay.
your sides are going to be reversed. Now, why this lateral inversion happened? The only reason behind the lateral inversion that whatever the rays coming from this mirror, okay, it is mostly from the perpendicular to the surface. Okay, whenever the light rays just strike on the surface and it comes out, and it's
Yeah.
mostly normal to that surface. So since the light rays are reflected normally from any surface, then we always have a lateral inversion. It means that our
Okay.
sides will be changed.
Yeah, lateral inversion.
Yeah,
Okay.
that is called the
And
lateral inversion.
also about the oh,
Hmm.
I think we did that, right? The
Yes.
construction and measurements. I think when we
Yes.
see past paper questions, we will understand more about it. We
Yeah,
can solve the
definitely.
questions also.
So which paper number?
No, I think we can do that later. First, we can go through the theory part and then
Theory
we can
part.
straight
Yes,
away.
that will be the straight away. Then we will start with the last portion. Okay.
Yeah.
because I already got the idea that how much things we have to cover. The only thing
Yeah.
is about the formula, okay,
Yeah.
which are quite less.
Yeah. They are.
Yeah, so that's also the quite easy for you also, okay, to
Like yesterday,
Mhm.
yesterday and today, I actually had a physics test.
Okay,
Yesterday, it was about just all the formulas of the year, like all the formulas we have.
okay.
And today, it was about circuits. The circuits test was really easy. It was just like normal addition of
Yeah,
parallel and
series
the
connections.
circuits. Yeah. And
Mm-hmm.
for formulas, I think there were only like
Mm-hmm.
22 or 25 formulas I had to learn for the whole thing, or like 30 or something.
Okay,
So I had to only learn like 30 formulas for the
yeah,
test.
that can
And
be
that's
done.
like everything in the portion.
Yeah,
So it was not too bad.
yeah, that's great. See, to remember all the formula, just try to speak the formula
Yeah.
instead of writing. If you just speaking the formula, okay,
Yeah.
then it will be more easy for you to remember
Yeah.
it. Okay, so this is about our plane mirror. Okay, then
Yeah.
next is what after the plane mirror?
It is reflection. No, it is
Refraction.
refraction of light.
Yes. Okay, let's start the refraction of light. So what is called the refraction of light? So whenever light is moving from one medium to another medium, then it always bending. So the
Yeah.
bending of light, when the light is interchanging its medium, okay, so that is called the refraction of light. So it's a bending of light. More precisely at the surface separating the surface separating two media. So at the surface of our two media, let's say this is our one medium and this is our another medium. This mu, okay, these are the symbol of our refractive index. Okay, because how we can consider that I have two different mediums. Okay, so the only identity that our mediums are separated from each other or different from each other, it is from this refractive index we can identify. So this mu is called refractive index.
Okay.
It's an optical property of any medium. Okay, it's an optical property. Optical property of any medium. But what will be decided by this optical property? So this optical property decide how much light will bend. Okay, when light enters in this medium's territory, okay, then how much light will bend. So that bending of
Yeah.
light is mainly depending on this optical property of any medium. Okay,
Yeah.
then we don't have such deep things about these optical properties, okay, like in what factors it is depending. Okay, and this always remember this is a fundamental property. Okay, this optical property, it's a fundamental property because see, like you also have a water is transparent as well as glass is transparent, yes or no?
Yeah. Yes.
But if you observe, if you just dip a pencil or a pen, halfly immersed, partially immersed, okay, then you will simply say that, or you will simply observe that the bending of pencil in water and that glass, it's totally different.
Yeah.
Okay, so this thing actually happened. So that is called the optical property of any medium.
Okay.
So let's draw a normal first. Now let's draw a light. Let's say this is my incident angle, theta I. So can I consider this is the actual path of the light
Yes.
where it was going. This is our actual path of light. But now since it's changed the medium, okay, so because of that, it start bending.
Yeah.
But how this bending works? Now, if this bending is like that, so consider this line as your normal line. Why normal?
Yeah.
Because it's a perpendicular to this mediums.
Yes.
So as you can see that it is bending towards normal. Can I say that?
Yeah. Yeah.
Now, since it is bending towards normal, so it means that this light ray is moving from rarer medium to denser medium if it is
Yes.
bending towards normal. So it's bending towards normal. Then this medium must be a denser medium. So this should be
So
a
if it's dense, it moves towards the
hmm,
normal, and if it's rare, it moves away.
yes, perfect answer. Okay,
Okay.
since it's bending towards normal, so it means it's a denser medium. And now if it is moves away from the normal, then it consider as a rarer medium. Like if we draw a diagram for it, let's consider this is the ray which is incident,
Yeah.
another new ray. So this is your new angle. Let me call this theta dash. So this is the actual path.
Yeah. But then it's moving away.
Yes, it will move away like this.
Okay, got it.
So this is called our denser to rarer. So whenever light moving from denser to rarer, it is bending away from the normal, and rarer to denser bending towards the normal.
Yeah.
Let me write down rarer to denser.
So does speed affect it?
Of course, dear, speed, wavelength, both are affected. That we will see.
Okay.
Okay. Uh, just give me a minute. Okay. Like I have too much cough in my nose. So just, yeah, just a moment.
Yeah.
Now I got relief. So if our light is moving from rarer to denser, then it bend towards normal, and from denser to rarer, from denser to rarer, it's away from normal. Got this point?
Yes.
Okay. Then now, your question was whether the speed of light is affected or not. Of course, it is affected. The formula for this refractive index, mu, is actually C over V. C is the speed of light in vacuum. Speed of light
Sir, sorry, could you repeat? Because like my internet is
Of course, dear.
lagging a lot.
Of course, dear. Okay. Now see, the formula for this our refractive index is actually C over V.
Okay.
C is the speed of light in vacuum, which is like nearly equal to 3 lakhs kilometer per second. So we mainly use 3 times 10 to the power 8 meter per second. V is the again speed of light, but in a medium.
Okay.
Again, it's a speed of light in a medium. This is how you can get your refractive index. Like, I have one question for you, that in water, light moving with 2.25 times 10 to the power 8 meter per second speed.
Yeah.
So can you just find out the refractive index of water and the speed of light in vacuum, that is 3 into 10 to the power 8 meter per second? Okay. But the thing is that speed of light in vacuum, I don't think it will be given to you in the question, because this is the understood part. Okay.
Okay.
So we don't have to worry about the speed of light in vacuum. It is always a fix, that is 3 into 10 to the power 8 meter per second.
4 over 3, which is 1.333.
Perfect answer. So, and now I have a refractive index for the glass,
Yeah.
which is 3 over 2. This is the refractive index of glass. Can you calculate
Okay.
speed of light in this medium?
Speed of light.
Yes, in this glass medium.
Okay. 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 So it's going to be.
Hmm?
Is it gonna be? Okay,
Hmm.
just a second. 4.5 times 10 to the power 8.
Can you repeat again?
4.5 times 10 to the power 8.
No, you did some mistake, because see, the light speed of light cannot exceed this 3 into 10 to the power 8 meter per second.
Okay, just a second then.
So
Just
just
a second.
yes.
I think I know. Um, mm, Wait, so
Hmm.
just a second.
Of course,
I don't think my answer. Um,
use this formula, mu equals to.
yeah. Is it? I'm either getting like something with 5 or 2. I'm not sure which is correct.
2 into 10 to
Okay,
the power
so
8.
yeah, 2 to 10 to the power 8.
See, this is mu equals to C over V. So this
Yeah,
is V, which you have to find out. So C,
so it's
if I
gonna be
substitute the value, 3 into 10 to
gonna
the
be
power 8, 2 will be multiplied here and 3 will be in denominator. So 3 and 3 will be cancelled. So you just got the answer 2 times 10 to the power 8 meter per second.
so it's just gonna be C over U.
Yeah, C over U.
Okay, got it.
Correct. Okay.
Yeah.
So as you can see that in this glass medium, the speed of light is more slower compared to the water. Is it or not? Like in water, we obtain
Yes.
2.25, while in glass, it's 2 into 10 to the power 8. Okay.
Yes.
So it means that this glass is more denser than the water.
Okay.
Okay. Like
Yeah.
if in a medium having speed of light is less, then that medium
That
is
means it's
considered as
dense.
a dense medium. Okay,
Okay.
because of that optical density, light is bending too much. So because of that bending, it just reduces its speed. And if bending is less, then it's optically a radar medium, then the speed of light is not changed that much.
Okay, got it.
Okay, great. So this is the overall concept of our refraction. Okay, so this thing happened during the refraction. Then now you have a refraction by sides. Yes. Yes or no?
Sorry, I couldn't hear you. My
Yeah,
internet's
yeah, not
still
an
not.
issue. Okay. Now
Could
you
you
have,
repeat?
yeah, of course, dear. Now you have refraction by side glass. Okay.
Okay.
So here is I have a rectangular glass slab. Okay. Now,
Yeah.
if I draw an incident light here, so we can consider
It's
this is
going
the,
to bend.
yes, definitely it's going to bend,
It's
but
going to bend. It's going to bend
mostly
uh,
always remember that.
towards the
Yes,
normal.
perfect. Always remember that.
Okay.
Like if you have nothing about the any information regarding mediums, then always consider that our light is passing from rarer to denser medium. That is our general scenario. Okay.
Yeah.
So why I'm just drawing this line too much long? So we can understood our topic. Okay. So this is the original path of the light, the actual direction or the actual path, the actual path. Let me consider a mu1, a mu2, another again mu1. Can I say that?
Yeah.
Now since it's bending towards the normal, so let me call it bends that much. This is
Yeah.
called bending or deviation. Bending, it is also denoted as a deviation.
Yes.
Okay, both have one and same meaning. So now it is deviated. Then here I can also draw normal. Now because this light is tried to emerge from this denser medium.
Oh,
Okay, and as you can see that it is moving from now denser to rarer or rarer to denser.
it is moving from denser to rarer.
So what happened?
It's gonna move away from the
Move away from the normal,
normal line.
like that. Can I say that?
Yes.
It is bending away. But the thing is, this our emergent ray or emergent light and the actual path, emergent ray and this actual path, don't you see both are parallel to each other?
Yeah.
Okay, and because since these rays are parallel, so initially my light was here from this point
It
instead of the,
travels in a straight line.
yeah, so that much shifting is there.
Yeah.
Okay, so this is called our shift, and because
Okay.
of this shifting, sometimes if you just observe from the glass left far by sides, okay, so you just you observe that the things are just little bit appear more on a height.
Yeah.
Okay, so this is called the shifting of light.
Okay. Got it.
Okay, and I don't think you have any formula for this shifting of light.
I have this. I have like critical angle and
Not
total
about the
in.
that is a different thing, critical angle and
Okay.
all. Okay, like if you want to remember the formula for the shifting of light, a little bit tricky formula. Do you have that formula or not?
If you can just say what's the formula,
Of course I can.
I might.
See, this is called your actual angle of incident, and this
Yeah,
is called your angle of refraction to the normal.
yeah.
Okay, this shift, this shift is denoted as an x, or you can denote by any of the other alphabetical word. This shift is equal to, and this t is the thickness of the glass slab which we are using.
Okay.
So it is equals to t times sine I minus r over cos r.
Oh no, we don't have it.
Yeah, and even though say by using Snell's law, okay,
Yeah.
that also just let me write down for you. The mathematical expression for the Snell's law is mu times sine of angle is always remains constant.
Yeah.
Like for the any medium, if you take a product of the refractive index with the light which made an angle with the normal line, okay, so the product of this two term always remains constant. So for this medium, if it is mu1 times sine I, then for the another medium, it will be mu2 times sine r. So you can also consider that this sine I over sine r equals to mu2 over mu1. Can I say that?
Yes.
One more formula. We know that mu equals to c over v.
So okay, so are there like
Hmm.
um so there's also something where it's if it's rarer you use this formula, but
Of
when it's
course,
denser, I'm
yes.
not
See, whether it's a denser medium or rarer medium doesn't matter. If you have a refraction, you can use Snell's law.
okay.
Okay, it doesn't matter. If you take mu1, then your angle must be in your rarer medium or in mu1 medium. And if you take mu2, then your angle must be in that mu2 medium.
Yeah.
Okay,
Okay.
now we know that this mu equals to c over v.
Yes.
So here it's sine I over sine r mu2, that is c over v2 for mu2.
What is mu2?
Mu2 is the refractive index of the second medium.
Okay, so the one which is emerging outside.
Yeah. No, emerging is the same medium. Okay. Through this glass slab.
So the one in the glass
Yes.
block is the second
Yes.
medium.
Yes. The glass block is the second medium.
Okay.
And one is we can consider simply air.
So sine over sine r is for
Mhm.
rarer to denser, and sine I no sine I over sine r is from denser to rarer, and
Yes.
sine I over sine r is from rarer to denser.
Perfect.
Okay.
Perfect. Okay. Now this mu2, that is the refractive index of this glass medium. So can I consider this c over v2?
Yes.
And for this mu1, it will be c over v1, because for this mu1, I can again use the same formula, mu equals to c over v, but since it's a first medium, so I'm just denoting as c over v1.
Okay.
So this both c got cancelled. This is in denominator, so it will move to numerator.
Yeah.
So can I consider I also have this kind of formula, sine I over sine r equals to v1 over v2.
So it's okay. So
Hmm.
okay, got it.
V1 is the speed of
So
light in medium 1,
V1 is the speed of light in
light,
one medium. V2
yeah,
is the speed of light in
light in
second medium.
second medium. Yes,
Okay,
perfect.
got it.
Yeah, so this is about the Snell's law, and this is the lateral shifting whenever you use any kind of glass slab. Okay, so the thing which are shifted away, okay, so that shifting you can simply calculate with the help of this formula, but luckily you don't need that formula. But remember one thing, about the questionnaire part, that the actual path and the emergent ray both must be parallel to each other.
Okay.
Okay, this is compulsory. Okay, so this is we can also consider that it's a like a condition.
Okay.
Okay, so this is a condition which has to be satisfied, that the emergent ray and the actual path of the light must be parallel. Since both are parallel, actual path and the emergent light are parallel, it also indicates that the actual path means the actually ray when it comes and this emergent ray both are in a same medium. Actual path and the emergent ray both are parallel to each other. Okay, so
Yes.
it means that we have actual light which we incident initially and this
Yeah.
emergent ray which we obtain in the last,
Yeah.
both must be in a same medium if they are parallel to each other.
Got it.
Got it? Can I give you
Yep.
one question? Of course, the tricky
Yes.
one. Okay.
Okay.
Okay. So you just tell me which two medium have a same refractive index.
Okay.
That is your objective.
Okay.
So let me give you a few mediums. Mu1. Just let me write down a little bit upward so I can get the proper space to draw the lines. Mu2, Mu3, and Mu4. So I'm just drawing this. These are the traces of path of the light. Okay. So which
Okay.
two medium have a same refractive index?
Same refractive index.
Yes, same refractive index. It is only possible.
U1 and U4
Perfect answer. Why?
because they're in a straight. Yeah,
Parallel to each other.
they're parallel to each other.
Okay. Now,
Yeah.
if I want to write down here now Snell's law, how I will write down?
So it's going Snail's law for which one?
Or for all of them.
Oh, okay. So Snail's law will be.
Just let me give you all the
Okay.
thetas. All the angles must be with the normal.
Okay.
So it's a product of the refractive index and the sine value of the given angle remains
Yeah.
constant. Okay, so
Yeah.
it's mu times. So for the first medium, if I consider mu1 times sine theta 1. So for the second medium, it should be
Uh,
mm,
Sine theta 2.
yes, mu2 times sine theta 2. Okay, then for the third medium,
Sine theta 3.
yes, perfect. So theta 2, theta 3, and for the last,
Sine theta 4.
okay. And it is experimentally verified by Snell and Format both. Okay, so we don't have to worry about
Okay.
it. Okay,
Okay.
this is the Snell's law. How you can simply just write down. And by comparing, if like any angles are given to you, then you can easily also find out your refractive index.
Yeah.
Okay. So this is about our Snell's law as well as the refraction and the shifting. Now we have a critical angle.
Okay.
It's so early, right?
Yeah.
But the thing is, like formulas are not given. So we are just studying the experimental observations.
Yeah.
Do you know what is critical angle? What do you denote critical angle? C or just like theta? Yes.
Critical angle will be the angle between the normal and the refracted light.
Mm, no, incident light.
Incident light. Okay.
But what is the speciality of this critical
But
angle?
then wouldn't the incident light and a normal light stay the same? Or is it the one where it's like perpendicular to each other?
Actually, in this critical angle, what happened? This is the certain angle when you incident your light from denser to rarer medium. Remember that. From
Yeah.
denser to rarer medium, if you
Or
just
medium.
incident, yes, your light, then the refraction of the light should be perpendicular to the normal, like this. If this is the normal, then this is the refracted light. It should be like this, perpendicular, normal.
Okay.
Okay, if this kind of refraction happens, then that angle of incident which we obtain in that denser medium, that is called the critical angle.
Could you just show the diagram?
Of course, I will show you here a big jumbo diagram that will
Yeah.
not only explain you the critical angle, but it will also explain you the total internal reflection.
Okay.
Okay, everything you
Yeah.
need you will get from this diagram.
Okay.
So let me draw first here a normal. This is called our mu1, a rarer medium, and mu2. Just consider big glass slab. Okay, and you are via incident a ray of light like this. This is my
Yeah.
incident ray.
Okay.
Let me call this my angle of incident is theta1. We know that it moves away from the normal like this.
Yes.
But now what happened if I increase the angle of incident? Then it will bending more away from the light.
Yes.
Okay,
If you increase the what?
incident angle.
Yeah.
See,
Yes.
always
The more,
remember that.
yeah.
Yes, always remember that in your rarer medium, your angle which is made by a light to the normal must be greater than the angle made by a light with normal in denser medium. So
So
the
rarer medium is greater than the,
rarer medium always have a greater angle compared to the denser medium.
okay.
So if I increase my angle of incident in denser medium, then in rarer medium, it must be increased to
Yeah.
satisfy its condition, to maintain its condition.
Yeah.
So let me again incident with little bit more angle. Now here you can see that I just increase the angle of incident here. Okay. So now this light will bend more.
Yeah.
Okay. Now let me further increase this angle of incident light. So as you can see now, I'm just getting increase and increase my angle of incident.
Yeah. Yes.
But this time now I increase at the certain limit. So I'm getting this kind of refraction.
Yeah.
Light is just parallel to the surface. It is also called grazing.
Okay.
Whenever we are moving parallel to any surface, it is also called a grazing effect.
Okay.
Okay, there are so many new words. Okay, in this total
Yeah.
internal reflection and all that we will learn. Like, of course,
Okay.
you know the about the mirage effect.
No.
No? Okay, looming
No.
effect.
No.
Not a single one. Okay, I will show you the
No.
pictures also. Okay,
Okay.
so now this is our angle of refraction. Can I say that? And it's a perfect 90-degree.
Yes.
Okay, so the angle of incident for which our refraction angle is 90-degree, that angle of incident is called our critical angle. Angle of
Okay.
refraction for which our angle of refraction is 90-degree. Angle of incident for which our angle of refraction is 90-degree. Okay, that
Oh,
angle of
wait. So
incident.
the angle of incident where the angle of refraction is 90 degrees is critical angle.
Yes, this angle of
Okay.
incident is your critical angle. Okay,
Okay. Angle of incident.
angle of incident for which refraction becomes 90-degree. Okay, so that angle of incident is called our
Critical angle.
critical angle psi. Okay, now if I want to hear Snell's law, can I use it?
Yes.
So mu2.
So it's going to be
Mhm,
sine R over sine I.
mhm. Now see, instead of I and R, here we will
So
use
you
this
can
C and
find,
R.
yeah,
You
C
can
and R.
find this critical angle. Okay. So this sine C, which is your critical angle. Now see, this R is going to be 90 degrees. So what is sine 90 degree?
Sine 90 degree. Wait, 1.
Yes, 1.
Okay.
So can I consider it's mu1 over mu2?
Yes.
Remember that mu1 is your rarer medium. Mu2 is your denser medium. Always.
Okay. U1 is
And
okay.
by chance or by mistake, if you take mu1 as your denser medium and mu2 as your rarer medium,
So,
okay?
sir, wait,
Mhm.
just a second. To
Yeah.
find the critical angle, it's going to be 1 over sine R.
Well, 1 over sine r, no, not sine r, because that r is 90 degrees. So it
Oh,
is
okay.
no use of
So
it.
1 and R is the same thing.
Yes.
So it's gonna be sine 1 over sine C.
Sine, can you repeat again?
C.
Sine c
Sine C.
equals to what?
Yeah. Critical angle. But then the
You can
critical
also
angle
write
is
down,
sine C.
yes, critical angle is sine c.
So in
You can
this,
also,
basically,
hmm,
sine R is refractive angle. Sine
yeah,
C is incident ray.
yes, incident angle. Okay,
Incident angle.
yes, incident angle.
So what are we finding out from this?
Well, we can find out the critical angle first of all, but our
But then
main
isn't the
purpose,
critical angle the incident ray, incident angle? So it's the
yes,
same
of
thing,
course.
right?
Yes, of course, it's the same thing. But see, but for not all the angles, like we can get this refraction is 90 degree.
Okay,
Okay.
but then if the refraction is not 90 degrees, then it's
Mhm.
just gonna be sine I over sine R,
Yes,
right?
yes, sine I over sine R. That way, at that time we cannot consider it as our critical angle. Now, see, this is the angle. Why we are finding this critical angle? So we can get the idea of total internal reflection. Okay. Without critical angle, it is not possible for us to get the
Okay,
idea
but
of.
then
Hmm,
if to find the critical angle, we need to use the 1 over sine C formula, right?
no, that sine c equals to 1 over mu. You can directly use this formula for the any
Okay,
medium. Okay, like if you have been given a medium glass having a refractive index 3 by 2. So sine c will be 2 by 3 since it's 1 over mu.
yeah, yeah.
Okay, so like that, you can simply calculate the critical angle.
Wait,
And
so U is refractive index.
yes,
So, okay. If you use refractive index, first we'll have to find refractive index
no, that will be
and
given to
then we'll
you
have to do.
always. Refractive index
Okay,
always given to you. Okay, so we don't have to worry about the
okay,
refractive indexes. They will be always given to
got
you.
it.
Okay, and if critical angle is given, then they can ask you to find out the refractive index.
Okay,
If c is given, then mu must be find out, and if mu is given, then mostly we are finding this c. Now
okay, got it.
what happened? Yeah, now what happened if I still increase the angle of incident? What happened
If
if I
we
still
still,
increase? Yeah, because see, now as you can see that in our ray optics, okay, especially in this chapter lights, we didn't get any angle which is greater than 90 degrees. It is not possible. Okay, since you got the refraction
yeah,
is 90 degrees, so it
and
means that
then
you
it's just
getting the
gonna
maximum.
reflect back. Yeah,
Reflect back in where? In the same medium.
yeah.
Okay, and if the all light is reflect back in the same medium, what is called? So now if my incident angle is greater than the critical angle, like if critical angle is 30 degree, then my incident angle, I can say 31 degree, 35 degree, 40 degree, like that.
Yeah.
Okay, so at that time what happened, the total light is reflected back, total light. Okay, so
Okay.
for this condition, our all light, or we can say that total light is reflected back. Since you got all the light reflected back, it
So
is called,
there's no refracted light. There's no
yes,
refractive ray.
no refracted ray. If all your light reflect back, that is called your total internal reflection. Okay, it is called our total.
Over there, you've written theta is greater than
C.
C, right?
Yes, this is
But
the
then
condition.
isn't, oh, okay.
Total.
No, wait. So over here,
Mhm.
theta of incident or refraction?
This theta is for the incident.
Yeah. But
All these
isn't the
thetas are
but then
incidental.
isn't the theta I and critical angle the same? Oh no, never mind. Because critical angle will only give 90 degrees.
Yes. Okay.
Okay.
So this is your incident angle. Okay. If it is greater than this critical angle, then all your total light will reflect back. That is called total internal reflection. But what happened if some of the light refracted? Along with this reflection, if some of the light is refracted, that is called internal reflection.
Okay.
Like some of the light, like this way, if they are refracted and some of the light is reflected. Okay, so you have refraction as well as reflection. If both of things are given together, it is called internal reflection.
Internal reflection.
Only the word internal reflection. But in total internal reflection, we don't have any refraction, only reflection.
Okay, got it.
Got it? So this is the idea basically for the critical angle. And with the help of the critical angle, we can get the total internal reflection. This total internal reflection we use in many ways. Like diamonds are sparkling. Okay. So
Yeah.
why diamond is sparkling? The only because of this critical angle. Okay. Since if the angle is getting lower and lower or getting minimized. Okay. Then for the
Yeah.
most of the incident angle, we are able to get the total internal reflection. And same thing happened with the diamond. In the case of diamond, since diamond has the highest refractive index, which is about 2.48.
Okay.
So diamond having the minimum critical angle, that is about 24 degree.
Yeah.
So because of that, whenever the light incident inside the diamond, okay, then this
Mm.
always satisfied this condition. Inside the diamond, this condition always satisfied up to the infinite time.
So in a diamond, light is basically being reflected everywhere.
Yes, everywhere. And it is perfectly internally reflected. Okay.
So there's no. So is it totally
Yes,
internally
totally internally reflection.
But then
Diamond.
if you were to keep a diamond on
Mhm.
if you were to keep a diamond on a table and reflect light towards it, wouldn't
Mhm.
you get some light outside as well?
Well, that is also happened. Otherwise, we are not able to see the diamond itself. Okay. But the thing is, whatever the light which is just moving inside the diamond, okay, it
Yeah.
will never come out.
Okay.
Since it is never come out, that's why it's called a total internal reflection.
Total internal
Yes.
reflection. Okay.
Otherwise, what happened? Like for the very certain angles, okay. So
Yeah.
only few percent of the light will reflect back from the surface of the diamond. Only few percent. Okay. But since those light which are enter inside the diamond, it will never come back. So that's why the diamond always having a sparkling effect, just like stars.
Okay, got it.
Okay. Then we can also use this total internal reflection, especially for this communication like optical fibers.
Yeah.
Okay. Then the mirage effect.
Yeah.
Okay. And the looming effect. So looming, that mirage and looming effect, that we will see tomorrow. Okay.
Okay.
But
Yeah.
mostly I can consider that tomorrow most of the optics part, means this light part, will be over.